Okay, so now that we have our end effector matching the end of the FK bone chain, and we also have the stretchiness of our bones being matched, we now need to set up the twist control so that we work out the rotation we need to apply to that twist control in order to match our FK bones. Once we've done that, that's going to be the complete matching IK to FK setup. So let's jump over to the whiteboard and in this video discuss some of the maths behind the approach that I'm going to take for working out that angle. Then in the next video we can actually implement the script that will generate the rotation that we need to apply to that particular control object. So I'm going to jump over to the whiteboard and let's start out by drawing what we're trying to find. We know that we've got the start of our bone chain, we have our upper arm going to our elbow, down our lower arm. We have our IK handle. We know that we have a twist axis that runs from the start of our bone chain down through our IK handle. From that axis, we know that we basically have a rest plane, and from that plane we rotate up to find by our current twist angle, and that's going to position where our elbow now is. So what we need to do, we basically need to construct two vectors, if you will, vector A and vector B. I'm going to say that vector A is our base. It's our base vector that we'd have from our central axis out to our elbow if we had a 0 degree twist. So let's say that A is equal to the base vector, base vector, when we have 0 degrees twist, and B is equal to the FK vector. That's the FK, a vector from the same point but up to the elbow of our FK chain. So B is equal to our FK vector. If we can find out the angle between those, that's going to allow us to work out that twist angle. So what we can say, to find the angle, we can use the dot product of two vectors. So A dot B is equal to the magnitude of A multiplied by the magnitude of B multiplied by cos of the angle between those two vectors. Now, if we make sure that A and B are both unit vectors, then that allows us to simplify this down to saying A dot B is equal to cos of theta, cos of the angle between those two vectors. So then we could take cos of that angle and we can basically invert it to get the angle itself. But what we're going to find is that the angle ranges between 0 and 180 as opposed to what we'd like, which is 0 through 360. With 0 through 180, we're only going to get the smallest angle between those two vectors as opposed to getting the sine of the angle, knowing if we need to rotate in one direction or the other. Now, we could use more complicated mathematics to calculate an actual angle value that would give us a true 360 degree range. But why use complicated mathematics when we could actually use some simpler mathematics and just be logical about it? We know we have the rotation. We know there is an angle of theta between these two vectors. We just don't know if we need to rotate in a positive direction from our rest position, our base vector, up to get that angle, or if we need to rotate in a negative direction down to get that angle. So we're basically sat with knowing that we have an angle between our vectors, but not knowing the direction of that angle. Do we need to rotate in one direction or in the other direction? So why not use a trial and error approach? What we can do, we can apply both a positive and a negative rotation and see which gets us closer to our target. We can tell that if this was a negative rotation and we rotate up in this way, this has now moved us further away than our target location. However, if it was in the correct location, if we were to rotate in the correct way, in the correct direction, we get closer to our target. So we can apply both a positive and a negative, see which gets us closer to our target. That is the FK vector that is our target. And then we know that whichever is closer is going to be the rotation for our twist control. Now things are still a little bit complicated because we need to actually find vectors A and B in the first place. We don't just have A and B to hand. Finding the tip ends of A and B is very easy. We know that the tip where for A is going to be our elbow position when we are set over to IK and set with a twist of 0. And we know the tip of B is going to be the elbow position in FK. It's finding the root end, it's finding the pivot point that sits on our twist axis. That's the hard part. Now, we could use a method similar to our knee setup, where we set up the twist control for our knee. We did calculate the pivot point. That is the perpendicular pivot point of what would effectively be our elbow in this case. So you could use that method, then reference the position of that null. However, I want to show a different method. So I'm actually going to show a mathematical method as an alternative to that. So feel free to either implement the other method yourself. You then have a null which sits on that axis. You could then reference the world transform of that null to get its position. What I'm going to do, I'm going to use some vector maths to actually calculate that position, just to show you guys something a little bit different. So what we actually have in terms of a mathematical problem is we need to find the foot of a perpendicular from the elbow to that twist rotation. So what we have, to the twist rotation axis, we've got our upper arm, we've got our lower arm with our IK handle, we have that axis, and we need to find the root of the perpendicular. There's the perpendicular, and that's the root. That is the point that we need. That's then going to give us our vectors that we can calculate angles with. So we're finding the root of a perpendicular from our elbow to the twist rotation axis. And there's actually a formula that will give us this. I'm not going to spend any real time explaining where the formula comes from, because that's beyond the scope of this lesson really. What I am going to do is basically give you the formula, show a diagram that helps explain the formula a little bit, but it basically works with the vector representation of a line, and it takes one vector and it basically projects that vector onto another vector, which is going to give us the new vector. We can basically take this vector here, project that down onto this vector here, and that will give us a new vector that gives us this position in space. So let's draw out a diagram of what we're dealing with here, and I think I'm going to bring up a new layer just to keep things nice and clean. So let's bring up a new layer, and with that new layer I'm going to draw out a very simple diagram that hopefully will help explain, and that is an awful line. So there we go, slightly better line. My straight line drawing ability today is not quite what it used to be. So let's go ahead and draw out what we have. We know we've got a line going from, this is our start bone, and this is our end of the lower bone. This is a point in space that we're trying to find, and we know that we're trying to find the foot of the perpendicular down onto this particular line. I am going to go ahead and just erase a few things now to clean up this diagram. I'm going to erase out the line representing our upper arm, since we don't need to know about that in this case. I am going to erase out the line representing our lower arm. Just recall, of course, that this point is our elbow position. So we've got that, and we know that we can define this line, this axis line, based as basically a vector representation of a line. That requires us to have a position vector going from the origin of our space to that point. I'm going to name that position vector A, and really that is just the position of that point. It's just expressed as a vector. It's called a position vector. We also can define B as a directional vector that points along that axis, and we know that because we can take our end effector and we can use the end effector and our start bone position, and we can work out a vector that points along that axis. Now B has to be very special. B has to be a unit vector, so I'm going to denote that with B with a hat on top of it. That means it has a magnitude, a length of 1. We want to make sure that B is indeed a unit vector. The formula will not work if B isn't a unit vector. We also have what I'm going to call, and that does point to the elbow. Please excuse that line being slightly off. This is another position vector I'm going to call P, and that gives us the position of point P, which is our elbow. Finally, the point we're trying to find is Q, and we have another position vector pointing up at Q. So we have various components, and what we can do, there's actually an equation for finding Q based on A, B, and P. So we can use A, B, and P, 3 pieces of information we know. We know the position of that point, the position of our elbow, and we can work out a unit vector that points along our twist axis. And the equation that we're going to use is Q is equal to A plus TQ dot B. And this is the first part of the equation, which is basically telling us that we have defined a line as a vector representation. That means we have a position vector taking us from the origin up to a particular point, and then we have any multiple of a directional vector taking us along that line. So A is taking us to a point on the line, TQ is our parameter moving us up and down the line. TQ needs to be a length, a directed length along vector B, getting us from point A to point Q. And to calculate TQ, we can calculate TQ using P minus A and dot that with our B hat, our B unit vector. Basically what that's giving us will P minus A is giving us that upper arm line, the line going from point A up to P. And if we do P minus A dot B and multiply that in with our line equation, what we're really doing here is projecting that line down onto our twist axis. That's giving us the length of that projected line onto the twist axis in the form of TQ. We're plugging that length into our equation for our line. That's taking us and giving us the actual coordinate of Q. So from that, we're going to have Q that is going to be the foot of the perpendicular. So just again to basically point out each of these components, A is the position of our shoulder, which is really the position of our upper arm, since we know our upper arm's origin is located at the shoulder. B is a unit vector, in the direction from the upper arm origin down to our end effector. So I'm going to say from upper arm to end effector. And P is our elbow position. So we have the three components we need to plug into this equation, and that equation will return to us Q, the position of the root of the perpendicular from our elbow to that twist axis. Now the good thing is, because we've already matched the end effector position and because we've already matched our IK stretch to our FK, that twist axis is always going to be the same, and because of the fact that we're simply doing a rotation about that axis with our twist calculations, that means the foot of the perpendicular is going to be the same as well. That means we only need to calculate Q the once, and we can use that to calculate all of our vectors that we need from Q out to various different elbow positions. So we do only need to calculate Q the once. Now again, we could calculate Q using a method of having a null, aiming at another null, offsetting pivot points, offsetting positions in this case, to give us a position that sits perfectly on that twist axis but perpendicular to our elbow. But in this case, I do want to use a mathematical approach just so that you guys get something a little bit different to what we did over with our leg setup. So with that, that's going to conclude a look at some of the maths that's going to crop up and the logic that's going to crop up in the next video. But in the next video, we're going to be creating the script that's going to implement this and finish off our matching IK to FK. So with that, that will conclude this video. Thanks a lot.